Perfect, very well. So happy to have Giovanni here, will be the first speaker for a progressive talk in which he will introduce the discussion about the use of, let's say, the limits and the constraints on Pauli exclusion principle transition, violating translation.
But anyway, let me, on behalf of organizers, to welcome Giovanni. So it's very nice having all of you here, even if we are not too many. That's the reason for which we plan to do next week a proposal to get him presence in Trento. And you have seen we have a restricted program, but rather ambitious and prestigious. And then let me introduce our first speaker, who is Giovanni, who is going, he already shared his slides. So I will, well, while Antonino is reconnecting, let me welcome Giovanni and all of you and leave the floor to Giovanni for his presentation. Thank you very much, Giovanni.
Thank you, Catalina. Thank you to all organizers. This kind of meeting is always a very nice idea. And again, in this season, let's say, these opportunities are better appreciated. What I'm going to do is really to try, and for some of you, these are things that you have already heard me say, apparently, but the focus is different from other presentations I've given on similar topics, because my main focus is on the law of composition of momenta and hypotheses, ideas, hints that might suggest that this law of composition of momenta is modified in the quantum gravity realm. And this, if true, would have implications everywhere, but particularly significant, and this will be very clear, and then the talk by Adazzi will make it surely even clearer. If there is a modification of the law of composition momenta, then the implications are particularly significant for the Pauli exclusion principle. But I will not say much about that. I will focus on the law of composition of momenta, also trying to put on the floor some scenarios which have not been yet considered from the Pauli exclusion principle perspective, and that I will argue they deserve being studied. So let me first, the crucial part I have to accomplish is to convince you about the motivation. To have a modified law of composition of momenta, I remind you, the law of composition of momenta we have right now is a manifestation of the invariance under translations of our laws, under, of course, classical notion of translations, but which is all we have ever had, and to argue that that should change is a very big step. So I will invest some energy into the motivation, and the motivation again is a bit indirect. I mean, what you can see rather clearly, though heuristically, but rather clearly from the structure of the quantum gravity problem are scenarios in which the Planck length becomes the minimum allowed value for wavelengths. And actually, that's where my journey started in this direction. I don't know how it was before 1990. I'm not that old, but in the early 1990s, I was a PhD student in the Boston area, and it was very fashionable for even the most prestigious colleagues to introduce in seminars on quantum gravity the remark that the Planck length would be the minimum allowed value for wavelengths. That was very puzzling to me, fascinating certainly, but puzzling because according to our current relativistic laws, a statement such that Planck length is the minimum allowed wavelength, since wavelengths are not invariant, can only be observer dependent. So it was very puzzling to me that these prestigious colleagues would make such a remark without then commenting on the implications for the relativistic laws. Shortly after, in the second part, the later years in the 1990s, it started to come out independently, just by calculation, not by conceptual exercise like I was doing. By direct calculation in some approaches to quantum gravity, started to come some results, particularly suggesting that the on-shell relation for particles might be modified. And so the issue of the fate of relativistic symmetries in quantum gravity came to center stage, not because of my earlier concerns about the minimum wavelength statement, but because of some results which were popping up. And the fate of relativistic symmetries became much of interest in the quantum gravity community. And initially, what was assumed is that the hypothesis should be that quantum gravity might, I mean, these are models, theories, arguments, so that we have no certainty, but the scenario that was worth studying was a scenario in which relativistic invariance was really broken. If you modify the on-shell relation, the easiest thing to happen, the simplest at least thing to happen, is that you break relativistic invariance. Then shortly after, a few years later, I realized that actually you could have this modified on-shellness and other similar results of departures from standard relativistic laws, which were emerging in some approaches, while preserving relativistic invariance. So this is a new class of relativistic theories with two relativistic invariants, not only a scale of speed, but also a scale of momentum, if you want, or a length scale, of course, an inverse momentum. And this, there has been a huge amount of more work over the last 20 years. We had a DSR 20 meeting just last year, and we really got to appreciate the huge amount of work that was done over the last 20 years to understand this new class of relativistic theories. And actually, for my older interest, it was very natural in such theories to have both a modified on-shellness and a minimum allowed value for wavelengths. Actually, the two things were connected by relativistic equilibrium. I mean, a relativistic theory is a theory of balance. You have relativistic invariance is balance among laws, and actually was intriguing to me to discover that there was some balance between my earlier concerns about the minimum wavelength statement and those results which had appeared a few years later on the modified on-shellness. How am I going to, so we have modified on-shellness, minimum wavelength. How am I gonna get the main topic of my presentation, which is a modified law of composition of momenta? This is very easy, especially if I discuss it in analogy with the previous transition. I mean, of course, that is previous and occurred. Now we are speculating. I have to remember continuously this thing. We are speculating about yet another relativistic transition, but let's learn from the previous one, the one from the Galilean, the special relativistic laws. And Galilean relativity, you know it very well, and is a relativistic theory without scales, without absolute scales. So you don't have scales to write formulae. This is just dimensional analysis. You could guess the on-shell relation of Galilei by dimensional analysis. You could guess that the composition of momenta was linear by dimensional analysis because you don't have a scale of momentum. And you could guess that the composition of velocities is linear by dimensional analysis because you don't have any scale in Galilean relativity. What changes then? Apologies, I forgot to switch off the phone. So what changes as you go to special relativity? Now you have one invariant scale, the speed scale, which turns out to be the speed of massless particles, in particular photons. And now with this scale, which however is one in my formula, but that is not important. It changes the dimensions of some of the, in particular, a momentum becomes an energy in units of C/1. Then you have a speed scale in special relativity, which is one more scale than in Galilean relativity. The law of composition of momentum remains unaffected, still linear. Again, there is there will be some subtle arguments, but it's obvious because by dimensional analysis in a relativistic theory, which only has a velocity scale, you cannot deform the law of composition of momentum. The on-shell relation is modified, and because with the speed scale, you can modify the on-shell relation. And of course, since you have a speed scale which is invariant, it actually plays the role of maximum speed in the theory. That is a big statement for velocity vectors. And in particular, I mean, I'm really upset. In most textbooks we feed to our students, all they see is the law of composition of parallel velocities, which is nonlinear, but that's not even far. I mean, not even close. Doesn't come even close to how virulent is the law of composition of velocities in special relativity. Because now you have this velocity scale, and nature takes over with its creativity. The law of composition of velocity in special relativity, and this will be important for what I'm arguing in the later part of the talk, is one at the border of what mathematicians would recommend the physicists to use. It's a law of composition which is non-commutative and non-associative. It has none of the two important cherished property that physicists love. And this is what happens when you add a relativistic invariant scale. Now, in this new class of relativistic theories, these DSR theories, you also have a momentum scale that allows you to have a further, becomes much richer the realm of possibility for the on-shell relation with this additional scale. And now the law of composition of momentum can and must be modified, must be nonlinear if the on-shell relation is modified. Why? Because boosts, the equation in the, you see my pointer, if I do like this, boosts, if the on-shell relation, if theory is relativistic invariant, must be an invariant relationship. So boost must commute, must have must leave invariant the on-shellness. So the boosts are deformed by the momentum scale necessarily. And now if the boosts have a dependence on this momentum scale, evidently, and this we see explicitly in all the explicit examples which have been constructed for these new relativistic theories, but you don't need the specific example because it's just by conceptual structure. With the deformed boost, the law of composition momentum, which must be covariant, gets deformed. So this is one channel through which you could envisage quantum gravity to produce a modified law of composition of momenta. I will not give you, I mean, if there are questions, I can do that, but I just advertised there is a toy model for all these, which works very well and has a number of mathematically clean property. This is a non-commutative space-time known as Kappa-Minkowski, where all the structures that I told you about are well understood. We also understood translations. Its funny symbols, epsilon, are non-commutative translation parameters, which are describing a translation symmetry of Kappa-Minkowski, which is a quantum symmetry. And we also understand that the law of composition of momenta is deformed because the notion of translation invariance is deformed. So there is a nice application of the ideas in this toy model, but there are others, although this one remains the most studied. For the first decade of DSR research, these were the basic tools. Then at some point, those working in this area, we realized that really we were working at an old Max Born idea. Max Born, in one of the earliest papers on quantum gravity in the 1930s, where only a few scientists, probably only Bronstein and Rosenfeld were thinking about it in those days, in addition to Max Born. Born was thinking about quantum gravity, and inspired by this duality, which of course was by this reciprocity that was very dear to him, he argued that inevitably, if we were to unify quantum mechanics and gravity, then momentum space should be curved. And we didn't know, but this was brought to us by some colleagues from Russia, actually after we started to realize that these theories with modified law of composition momentum could be described as theories on a curved momentum space. Let me skip this. This is just to tell you that now, over the last decade, we realized that several results in quantum gravity could be a posteriori understood as a realization of this idea by Max Born in the 1930s. And perhaps most importantly, the only quantum gravity we really can solve, and it was a huge effort lasting 20 years to solve it, but dimensionally reduced 2+1 dimensional quantum gravity, we now feel we have a good understanding of it. It's a much simpler theory than for the quantum gravity, but it's pretty complicated theory nonetheless. Took 20 years to understand it, but we now understand it, and it clearly is a theory with a curved momentum space, with DSR deformed relativistic symmetries, with modified law of composition of momentum, and all that. And yes, you can look at this paper in Physics Review Letters by Friedel and Levine. Is perhaps the most pedagogical introduction to understanding 3D quantum gravity and its curved momentum space and the DSR relativistic properties, and the modified on-shellness with also a modification of the law of composition of momenta. Why do I mention curved momentum space? And I'm trying to get to the law of composition possibility, because the geometry of momentum space over the last decade has become really it's guiding us in the realm of possibility for this new kind of relativistic theories, which we call DSR. And so we phrase the key relativistic properties in terms of geometry of momentum space, and we basically know that the realm of possibility which is out there for us to explore has to do with the choice of the geometry of momentum space, which will be a Riemannian geometry. And if it is going to be relativistic, it will be maximally symmetric, but the affine connection is not necessarily, typically is not the metric connection. So there is a certain realm of possibility for the possibilities for these geometries of momentum space. The on-shell relation we phrase in terms of the metric on momentum space is given in terms of the geodetic distance on momentum space. And the law of composition of momentum, which is my main objective today, is basically connected to the notion of parallel transport on momentum space, as this figure tries to suggest, at least evocatively. And we give the law of composition of momentum in terms of what is the affine connection on momentum space. And again, I stress the affine connection for example, for this Kappa-Minkowski example, toy model, we now know very well which metric and which affine connection on momentum space corresponds to that model. And the affine connection is not metric, is relativistically compatible with the metric, but is not a metric connection. And this actually happens in all cases where the momentum space is a group manifold, which is the the family of momentum spaces choices that Kappa-Minkowski fits in. This idea of curved momentum space from these formulas might be just, you might see it understandably as just an attempt of interpretation. I'm not producing predictions. I'm just rewriting, for example, in this case, the on-shellness and the law of composition of momenta in geometric language. So you might find it cute, but not particularly valuable. But it is valuable. For example, it's not what I want to talk about today, but there is a strong line of research in phenomenology which has to do, we used to say the energy dependence of the speed of massless particles in these new relativistic theories. And it was the result of in each model, we had to do very complicated calculations, often disagreeing by just missing a factor 2 somewhere. And we now understand, through this geometric story, we now understand that this was dual redshift. Actually, this time of travel phenomenology that has been done for now 2 decades is really study of dual redshift, is redshift of momentum space. I don't want to take too much time to my talk, which today is aiming for other objectives, but it's really well understood as dual redshift, and it is computed now straightforwardly as dual redshift without the pain of other paths toward computation. Let me just stress again, today I will skip, which is hard for me, but I will skip this phenomenology of time travel studies. But let me just advertise, those of you who don't know it, this is really a case where we have Planck scale sensitivity to effects. So what I was calling quantum gravity phenomenology already 20 years ago now really exists, and actually is a large branch of physics which I'm keeping updated in my living review, and where at least some of the studies of the Pauli exclusion principle also belong to. So now, what is the situation? So we have this momentum space structure on one, geometry on one side, which from the point of view of things like the Pauli exclusion principle would have its most significant manifestation in the law of composition of momenta. And there are 2 scenarios which I want to stress. First, I remind you, however, that when we went from Galilean relativity to special relativity, when we introduced the first relativistic invariant scale, the law of composition of velocity went crazy. I mean, it's a law which is non-commutative and non-associative. So we are even prudent when we assume that only one of these 2 might be lost. But at present, when we study these curved momentum spaces and these DSR relativistic theories, what we are trying to accomplish is to beginning as an initial exercise to understand what happens if you lose the commutativity of momentum composition law or its associativity, not both together, which however it's also, we already know of some geometries of momentum space that do that will produce momentum composition which is non-associative and non-commutative, but much of the work actually has been on the case where the law is still associative. I mentioned Kappa-Minkowski. And also from what I've seen, most of at least some of the arguments motivating Pauli exclusion principle research have been inferring estimates from the Kappa-Minkowski and other group manifold momentum space, I would call them, DSR relativistic scenarios. And these are by construction situations which law of momentum, law of composition of momentum is still associative, but non-commutative. And conceptually, it's important to know that they are in that little box of non-commutative but associative composition laws. much less has been done for commutative but non-associative laws of composition of momenta. There is some works. I mentioned a couple of examples here, but not much has been done. I don't think any of it has inspired, for example, Pauli exclusion principle research. It's actually not obvious that it will, as I will comment later, because as long as it is commutative, is not in, whereas non-commutativity immediately brings a challenge to the Pauli exclusion principle. Non-associativity might be more subtle, but I think it would be very important. This is one of the main arguments I'm pushing forward today. I think it's very important trying to understand what happens to the Pauli exclusion principle when the composition law is still commutative but non-associative. Something rather subtle might happen in the structure of Hilbert spaces and then the implications for the Pauli exclusion principle. When the law of composition of momenta is non-commutative, it's very clear that something goes wrong for the Pauli exclusion. Goes wrong. I mean, that some modifications are needed for analysis of the Pauli exclusion principle. And this is because non-commutativity of these, I'm using some equations which I borrowed from a presentation by my colleague Michele Arzano. The Pauli exclusion principle and our tests of the Pauli exclusion principle are directly related to the spin statistics theorem, to the fact that you know, you need to anti-symmetrize certain states, or for bosons you would have to symmetrize them. And let me just make you notice that something funny happens in a theory with the non-commutative compositional momenta when you do a bosonic state, and the counterpart of this will happen to fermionic states. Because you see, for example, the top equation in this slide, it would be a case where I symmetrize a symmetric state obtained from two states of momenta K1 and K2. And this, in special relativity, would be an eigenstate of momentum, but it's not an eigenstate of momentum if the composition law is non-commutative. For example, here I'm using, or Michele Arzano, who lended me this slide, was using indeed this famous Kappa-Minkowski composition law, which has these exponentials in the modification of law of composition. And you immediately see that then you need, in order to have a state which is an eigenstate of total momentum, you need to modify the symmetrization rules. And in general, there will be, for two particle states, there will be two states that are equally likely, but they are different, but they are equally likely candidates for being the description of a two-particle symmetrized state. And of course, analogous issues arise for anti-symmetrization and therefore the Pauli exclusion principle. So this is the status of what has been done from this point of view. For the most studied scenario of the SR relativistic theories, the one with associative but non-commutative composition law, we are still stuck to realizing that something new must be done concerning symmetrization and anti-symmetrization of states. But the last time I checked, there was still not a consensus of what exactly should be done. And two of the great experts of this now widespreading debate are indeed Antonino Marciano and Michele Arzano, who might want to update us on recent development. It remains a bit hard to understand what to do with these issues for symmetrization and anti-symmetrization. I think correctly, for example, in works by Dazzi, by Marciano, in spite of these present inability to move much forward in the understanding of the modification of the Pauli exclusion principle that these new theories would require. Some valuable phenomenological models have been emerging and are being studied, and experiments are placing limits on these models, and this will be much help also for the theory work. What I stress again in closing is that I think it would be beneficial if a similar effort was done also for the complementary possibility, the one of commutative but non-associative composition laws. I mean, I think, again, in fact, this commutative might suggest that it doesn't give you, surely it doesn't give you the same problems for the definition of bosons and fermions, but the fact that it's non-associative, and if I start thinking maybe of three bosons and three fermions and their relation to two boson states, or the non-associativity, I'm really curious, and I think would be a major breakthrough to understand, even just in principle, even if nature doesn't do it, but conceptually to understand what is the quote-unquote price to pay for a non-associative composition law. And somewhere I smell that something like the Pauli exclusion principle might be affected in ways interestingly different, but probably equally significant or comparably significant to the case of non-commutative but associative composition laws. And this is all I had intention to say. So thank you.
Thank you very much, Giovanni. Thank you. Can you hear me?
Yes. Yes.
Okay, very well. Thanks a lot, Giovanni, for this wonderful start for this workshop. So I would say if there's any question now, a couple of questions, and after we will have an extended discussion. But if we have any question now, I mean, I think that we have time for a couple of questions for sure. Yes, I see there's Giorgio that wants to ask a question.
Yeah, from sort of quantum field, from sort of at least Peskin and Schroeder, I'm not an expert. The spin statistic theorem emerges from a stable vacuum, right? I mean, if you impose commutation relations on fermions, you will not have a minimum of energy. Then you will have tachyons and whatnot. And to have a minimum of energy, you need anti-commutation. How stable is the statement with respect to this curved momentum spaces?
Oh, that's a very good direction to think about. I mean, what we have learned in these 20 years of studying, and now it has been done by a very large community, and from different angles, but it always comes to the point of understanding how the old notion is deformed. So we are not able to study yet these theories, the stability of vacua, but that would be probably a very promising direction. You need to learn to ask the question. There are some equivalent ways in which you could ask the question in our present theories, but usually we then discover that one of those ways is more efficient in letting us understand what's the next step. So you could go that direction. What replaces? We are looking for deformed symmetrization and deformed anti-symmetrization. This is very clear from the mathematics. But what is the right notion might be just related to some argument like the one you mentioned. You might test different such notions, and there are a few already in the literature, and test them on the basis of the stability of the vacuum. And that might tell you which deformation of symmetrization and anti-symmetrization is to be preferred.
Okay, thank you. Okay, thanks.
Okay, I would say if there's another question, we have time for another question before moving to the next speaker.